So I was assigned the task of talking about numerical relativity, and that was too big, so I'm going to restrict myself just to talking about simulations of black holes and neutron stars. And as you all know, this is a very special year because we're celebrating the 100th anniversary of this paper where Einstein first wrote down the field equations. But it's very special for another reason as well, which we also heard about this morning, namely that this is the year where Advanced LIGO has started its science run just over a month ago. And finally, we're at the stage where within maybe the next 2 to 3 years, we should begin to expect to have detections. And so what I want to focus on is how the simulations have fed in and will continue to feed in to gravitational wave detection. So just to remind you, gravitational waves come in two flavors, two polarizations, and their effect on, if you had a circular ring of test particles, right, it's a quadrupole distortion where the one axis gets compressed and one expands, and then half a cycle later it reverses. You'll notice that the two polarization states are rotated at 45 degrees to each other, not at 90 degrees as for electromagnetism. And exercise for the graduate students and postdocs, why is it 45 for gravitational waves and 90 for electromagnetism, right? The faculty don't have to do this, it's too difficult, right? Okay, so we heard the effect on the detector can be characterized by an amplitude h, which is the strain, just the delta L over L of this distortion. And LIGO is, roughly 4 kilometers long, the arms. I'm going to, I thought that Nergis was a little optimistic saying h of 10 to the minus 21. I think most astrophysicists would say it's more like h of 10 to the minus 22 that we're going to need. So this is a delta L of 10 to the minus 16 centimeters, which, remember, is 1/1000th the diameter of a proton. All right? That's what these people claim they're going to measure. Or 10 to the minus 12 of the wavelength. And when you first hear about this, your reaction is this violates something in freshman physics. I mean, right, it's impossible, right? How are they going to do this? Well, Nergis explained it, but I have a simpler answer, right? Sorry, it's a miracle, okay? So we'll leave it at that. All right, now why is numerical relativity relevant to this enterprise? So, two reasons. One, the obvious one, when they detect something, we would like to know, was Einstein right? Does it agree with the detailed predictions of the theory? In order to answer that, we have to know what the detailed predictions are. But secondly, we can actually improve the sensitivity of the experiment by carrying out simulations. That might sound counterintuitive. I'll explain what I mean by that in a minute. All right, so first of all, comparing theory and experiment. What could we learn if we actually had a detection? So, black holes have become so passé. It used to be that there would be a newspaper article, astronomers discover black hole in some galaxy, and it would get on the front page, then it moved to page 5, and then it would be a little light. Now they don't even put it in the paper anymore, right? When you read that a black hole has been discovered, that is not true, okay? What the astronomical observations tell us is there are regions in the universe, for example, we know a few dozen cases with stellar mass objects where this is true. There are regions where there is a lot of mass in a small volume. If general relativity is correct, then it must be a black hole. Okay, but there's a big if there. And we don't have any direct independent observational evidence that the theory is correct in the regime of strong field gravity where black holes are relevant. Right? So even the beautiful Hulse-Taylor results, they only tell us about the behavior of the theory in a relatively weak field. I'll make precise in a little while what I mean by weak field, right? But it's not testing the ultimate strong field predictions of the theory. Okay, so are these the black holes of Einstein's theory? Is space and time warped in this peculiar way that black hole geometry predicts? We don't have direct tests on that. We really are like the astronomers in the cartoon, right? It's black, looks like a hole. I'd say it's a black hole. Okay. So we need black holes. We need some kind of probe that will come from the strong field region to our detectors on Earth, and that's LIGO. So if we want to detect the waves, there's a conventional way of splitting up what we might see. So here, the artist is Kip Thorne. You'll see these black holes depicted as these whirling tornadoes, the dragging of frames of the spin of the black holes. And so we have an early region, which is marked known. There we can predict the waveform by using perturbation theory, right? It's just the first order corrections to general relativity, sometimes called the post-Newtonian approximation. The final stage, when two black holes have merged into a single object, that object oscillates a little bit, basically like the ringing of a bell, and emits some waves, and then settles down to a stationary black hole. And that we can also do analytically using perturbation theory of a single black hole. Right? In fact, that was my PhD thesis. But in between, we have no small parameters. We have all the messy complications of the nonlinear PDEs of general relativity, and the only way to match these two regions together is with computer solutions. Okay, now how do we improve experimental sensitivity? Well, let me remind you how LIGO actually will detect these signals. And the idea is to use what's called matched filtering. So imagine up at top we have the result of some computer simulation or some analytic prediction for a particular gravitational waveform. In the second panel, I've buried that gravitational wave signal as that tiny little red thing in a huge amount of noise. And you might think that it's impossible to detect that signal buried in so much noise. But in fact, because we have a prediction, because we know the shape of the needle we're looking for in the haystack, all we do is we cross-correlate that template with our signal, and every time there's an up in the template that matches an up in the signal, that will give us a positive contribution. And similarly, every time there's a down, it matches with a down and gives us another positive signal. And so we get a spike that's shown with this arrow here. Whereas where we do the cross-correlation with the noise, on average, the ups and the downs cancel out. And that's how we're able to pull out a candidate signal of much smaller amplitude than the actual noise in the detector. Okay? So in order to do this, we need good templates. We need to know what kind of signals to look for. And that's where the simulations come in. So if we could have, now we can't do enough simulations, they're very expensive, they take big computers. We can never hope to do this whole thing numerically, but what we can hope to do is to build up analytic or semi-analytic models, template models, and then calibrate them against the numerical simulations. So that's where we hope to make a contribution. All right, so this nice figure, which is done by Beverly Berger, shows the improvement, the small little sphere in the middle that's marked LIGO. This shows the local universe centered on the Earth, and it shows the reach, the range out to which LIGO would see, say, two neutron stars spiraling in together. And then the big sphere shows you 10 times greater range, advanced LIGO, when it reaches its design sensitivity in a couple of years. And this volume then is 1,000 times bigger, and that's why we expect the event rate to be 1,000 times greater and gives us some confidence that we're now in the regime of astrophysical expectation. We're actually running a betting pool at our relativity lunches on, if anyone wants to contribute $5, you pick a date, and you tell us the closest to the date of the announcement will get the pool. I'm collecting money after the talk. Okay, so how do you solve Einstein's equations? Well, the problem was, until 2005, I should back up and say, it was in the sort of the 90s, about 1992, 1995, somewhere around there, that computers got big enough that it became feasible to attempt to solve Einstein's equations numerically in full 3 spatial dimensions. And everybody who tried the problem found that the simulations were unstable. And there was a lot of argument in the community about why this was, bad numerical methods, coordinate conditions, all kinds of things. And then we showed that, in fact, the cause of this problem was not because we didn't know how to do numerics. It was actually more subtle. It's a thing called constraint violation that I'll explain in a minute. But basically, plotted on the y-axis is a constraint, a quantity which should be 0 if you're solving the equations correctly. And this was done in this plot for a number of different numerical resolutions. And you can see as the initial error goes down, you keep that value constant, and then your simulation blows up. Right? You see the exponential growth. And if you extrapolate that back to t equal to 0, you'll see it intersects the axis at 10 to the minus 16, which is exactly numerical precision on a computer. So what this is saying is the cause of the problem is that you are trying to solve a mathematically ill-posed problem. Even a 10 to the minus 16 error at t equal to 0 will grow exponentially fast and lead to a blow-up. Okay? And what I want you to note is the size of the errors on the y-axis, right? 10 to the minus 5, 10 to the minus 9, all the way down to 10 to the minus 12. And if anybody of you have worked with solving 3-dimensional PDEs in time, you wonder, how do you achieve these accuracies? Okay, and that'll be a theme that I'll come back to. Okay, so let me explain what constraint violation means. So Einstein's equations, you have a symmetric tensor, G alpha beta. It's got 10 independent components. And there are 10 components to the Einstein equations, right? 10 equations, 10 unknowns. But the problem is there are 4 degrees of freedom to make arbitrary coordinate transformations. So you have an overdetermined system. There are only 6 physical degrees of freedom there, but you have 10 equations. And humans are actually notoriously bad at solving overdetermined equations. Nature has no problem, right? She's smarter than we are. And this is what actually leads to this instability. Now, this is well known also in Maxwell's equations. I don't know why we don't teach this in our courses, but anyway, it's a fundamental property. Let me remind you with Maxwell's equations, which are simpler. So here's half of Maxwell's equations. The divergence of E is 4 pi rho, and then there's an equation for propagating E forward in time. So you could imagine setting this up on a computer. You choose an E field that satisfies the first equation, the constraint, and then you evolve it forward in time with a second equation. Right? And then, as an easy exercise, if you take the divergence of that second equation, you can see that it will guarantee that if the constraint was satisfied initially, it remains satisfied. Well, that's an analytic guarantee. It doesn't mean that if you try to solve this numerically, that constraint will remain satisfied. And in fact, it typically doesn't. This is a problem well known to plasma physicists. And there are lots of techniques that have been developed for dealing with this. Okay, so here's just the proof and similar thing for the divergence of B. So you need some special numerical techniques. And the problem is that these techniques don't work for general relativity. right? Until 2005, when our chairman was the first to show how to do a stable simulation in 3 dimensions. And this really did revolutionize the field. All of a sudden, these calculations became feasible. Other techniques, once you know that it can be done, people work harder, and they found other ways of solving this too, and it sort of threw open the whole field. There are now about 10 or so groups around the world all working on different aspects of this problem. So the results that I'm going to describe come from a collaboration. SXS stands for Simulations of Extreme Spacetimes. And this started out from our group at Cornell and now has spread around to a various bunch of institutions. Now, I showed you that slide which showed that very high accuracy with which one could solve these equations. And how is that done? So the answer is you have to use high-order numerical methods. So let me remind you, most physicists only know one numerical method, right? Finite differencing. If I want the derivative of some function on a grid, I take its value here, I subtract, divide by the distance, that's the derivative, okay? Suppose I want a higher order method. Well, if I want the derivative at that centered point, I can do a Taylor series expansion, and then I can use the values at a wider and wider stencil of points to estimate the derivative at the center. The problem comes when you run into the edge of your grid. You can only have points on one side, and one can show that if you do this finite differencing technique, the coefficients in the expressions get bigger and bigger, and they have different signs. So you're trying to estimate a quantity by canceling larger and larger numbers, so it doesn't work. There's an answer to this called spectral methods, and the basic trick is you don't use a uniform grid. If you cluster the points in a very clever way towards the edges of the grid, you can estimate all kinds of numerical quantities like derivatives to higher and higher order, in fact, the order of the number of points you have, and achieve high order results. Okay, so now, just like quantum mechanicians or mechanics or whatever the word is, people who do quantum mechanics switch back and forth between position and momentum space, you can do the same thing here. Go from that spatial representation to a representation, a transform. It's an expansion in basis functions, like you learn about when you do separation of variables. And so the spectral method just says, I get the unknown coefficients, those fk of t's, by just doing a projection. And Lanchas, who also made contributions to general relativity, showed a long time ago that if you're very clever, you can make this a discrete transform. And so we have this way to go back and forth between n collocation points where we sample the solution and the coefficients of our expansion in a sum of basis states. And this method has the advantage that as you increase the resolution, the number of grid points that you use, for a smooth function, you can approximate it exponentially fast, faster than any polynomial. And that's the secret to getting the high order accuracy. Okay, so when we want to have black holes on the domain, one way of handling the black hole is basically to say, well, black hole has a singularity inside. I don't want that on my computer. But no information can propagate out from the black hole. So I can excise a region in my computational domain that contains the black hole. I don't need any boundary conditions. Nothing is coming out. That's tricky if I'm doing finite differencing, right? How do I adapt my stencil around there? It's even trickier if I'm doing spectral representations, because in the spectral representation, I use all of the points in the domain to represent the function. Now I want to cut off some piece. How am I going to do that? Well, I don't know how to do that. The way we came up with handling that is basically to introduce a second coordinate system. Basically, if you imagine a binary, say of two black holes, go to a co-moving coordinate system where the black holes are at rest. If the black holes stay at rest, I can set up a computational domain that is fixed and make sure that the edge of the domain is on the surface of the black hole. I never need information from the inside. Now, in order to do that, I need a mapping, a time-dependent mapping that goes between my co-moving coordinates and the physical coordinates that are inertial coordinates at infinity. How do you do that? Well, we borrowed something from the engineering literature, which is control systems. Basically, what you do is you measure the position of the black holes, how much it's moving in time in your physical reference frame, and use that, so that's an error that you then feed back into the mapping to keep the computational grid stationary. And here's a picture. On the left is the computational domain where the black holes remain stationary, and on the right is the physical inertial frame, which you can see these highly distorted objects just about to merge. Okay, and this is all, the fact that it looks like this and not somewhat different, that's just the choice of the coordinates, which we've heard a lot about, right? It's not physical, but it's the coordinates that we use for the calculation. All right, so let me describe some results. So here is an early result from our collaboration, the simplest case of equal masses, non-spinning, spiraling in, 15 orbits. And just to give you an idea of the power of using these spectral methods, with just the equivalent of 46 cubed points, which is, for people who do finite differencing, that's nothing, right? It's a very small resolution. The error in the phase of the wave at merger is about a radian. If you go from 46 to 67, not even a factor of 2, you get down to 0.003 radians. You're seeing the exponential convergence. Okay? So having this kind of efficiency has enabled us to carry out many, many simulations and toward this goal of producing templates that can inform LIGO. All right, so here's the waveform that you see. The early part is sort of this post-Newtonian part. Here is the region near merger expanded. And it's kind of boring. It's a chirp signal, but it's boring because we took a symmetrical situation, right? Two equal mass objects, no spin. But already with this, you could do something interesting. I mentioned that in the early phase, there is this post-Newtonian approximation. And the people who've worked on this know that it's a notoriously ill-understood approximation. Right? We don't understand the rate of convergence of this series. So here's an example. In the first line, I've written down the acceleration, say, of body 1. You can see it's just g times the mass of body 2 over r squared. Right? That's Newton. Now, using Einstein's equations, you make a power series expansion in the v squared over c squared of the orbit, right, which is related to the m over r. And you get this post-Newtonian correction. If you work very hard, you can get, you'll see the 1 over c to the 4th, and then 1 over c to the 5th. This is the term that actually has it's the radiation reaction force from the quadrupole formula. And you can keep going, right? And that's where we stop, right? Right now, the calculations are only done up to 1 over c to the 7th, right? People are still working on the 1 over c to the 8th. Well, we can now answer the question, how good is this? So you can take this approximation. By the way, there's no spin in this. There's more terms if you put the spin in. And you can turn this into a prediction for the phase of the wave that's measured at large distances. So here it's parametrized by this quantity x, which is related to the orbital angular velocity of the particles, which is v squared over c squared. And you'll see that x to the minus 5/2, that's the term that you get from the quadrupole approximation. And then all these other terms follow from the higher order post-Newtonian expansion. And you can see it's horrendous, got logarithms, all kinds of stuff. How good is it? Well, we now can tell you the answer. So here's a comparison, the difference between that prediction for the phase of the wave from post-Newtonian theory and from numerical relativity. And you can see when, and it's probably best to look at the top scale, this is the number of cycles of the gravitational wave before merger. And you can see that initially the error is very small, but that as you approach merger, somewhere around 4 to 8 cycles before merger, it gets bad. So you tell me the accuracy with which LIGO is going to make this particular measurement, right? And then I draw a straight line across, and then I can tell you up to what point the post-Newtonian approximation is good, and then after that you have to use numerical relativity. Now, this is actually the most favorable case for the post-Newtonian approximation. It turns out that as soon as you add spin to the problem or the mass ratios become unequal, the post-Newtonian approximation rapidly gets much worse. And instead of 4 to 8 cycles before merger, it can actually be hundreds of cycles, where our current knowledge of the theory is not good enough. So we need to be able to do numerical simulations. Well, we either need the analytic people to get cracking, or we need numerical simulations that extend to large mass ratios and large spins and can do long simulations. Okay, so here's an example. This is a random case, for relatively large spins, 0.9 of the maximum, mass ratio of 6 to 1. You can already see these are the two polarization states, that the waveform is highly modulated, right? All kinds of interesting phenomena. So in principle, if LIGO could measure a waveform like this, we can use our knowledge of the templates to work backwards and infer those parameters, the mass ratios and the spins and so on, of the parent object. All right, so our collaboration has put out a public catalog. You can go to blackholes.org and you can click on one of these cases and you can look at the prediction of the waveform. And these are being used to build template models and so on. And here's our 174 ones. Okay. So let me show you just a little movie. Oops, sorry. All right, so this is this case of the 6 to 1 mass ratio. And you'll see it already in one orbit, you can see the precession effect. So the gravitational interaction has a spin-spin and a spin-orbit coupling, just like electromagnetism in quantum mechanics, that shows you, in this case, the precession is even greater than 90 degrees. Okay? Completely non-Newtonian effect that comes from the coupling of the angular momenta in the problem. And at the bottom is the complicated waveform, right? So you remember this is an to a certain numerical precision, it's an exact solution of Einstein's full theory, right? That's predicting not only the trajectories of these black holes, but also the waveforms that are produced. All right, so I want to talk quickly about neutron stars. So in addition to black hole collisions, we expect there should be neutron star binaries, and also black hole and neutron star binaries. And these should be not only sources of gravitational waves, but they're one of the prime candidates for explaining short duration gamma ray bursts. Here's a profile of gamma rays, and the fact that the time scale is much less than a second is what people mean by short. All All right, so you need full general relativity to do this, but in addition, you need all the complications of relativistic hydrodynamics. You need to put in neutrino physics, magnetic fields, all kinds of stuff has to go in to do this right. We're not close to being able to do a complete simulation. We can do pretty well on the gravitational waves, because that's just the bulk properties, but if you want to relate this to the other kinds of physics that might be observable, we're still quite far from being able to simulate that. So this leads to a tie-in between experiments like LIGO, which will measure gravitational waves, and electromagnetic and neutrino measurements that can be done with satellites and telescopes. And this is sometimes called multi-messenger astronomy, this idea that we will learn about these phenomena by tying together all kinds of possible observations. All right, so our code is called Spec. So on the left is some technical stuff about what goes into this code for the aficionados. But the only thing that's relevant here is the accuracy, or rather the lack of accuracy, of these calculations. So the problem is that those beautiful spectral methods that work for the smooth problem, mathematically smooth, no discount, no shock waves, for the binary black hole coalescence, as soon as you have matter in the neutron stars and you can get shock waves, the spectral methods no longer work. Okay? So these calculations are done also with finite difference methods. And the gravitational wave phase is, at best of order a radian maybe at the time of merger. The accuracy of the matter simulations, maybe 10%, something like that, sort of the state of the art. All right, I was going to show a movie, but I'm actually going to skip over that. It's not so interesting, because I want to get to something which is sort of relevant to looking to the future. So all existing codes in computational, not just relativity, but computational astrophysics, have this problem that they're limited in their accuracy. If we project ahead as computers get bigger, what's kind of the realistic resolutions we might be able to have, what kind of accuracies can we expect? Probably we'll be able to get down routinely to 1%. Now, if you're an astrophysicist, you'll say, well, surely for astrophysics, 1% is more than enough, right? I mean, who needs more than 1%? Well, the problem is that there are some of the most interesting problems in astrophysics actually need better than that. And let me give you some examples. So if we want to get to better than 1%, the problem is that the current methods won't scale up to take advantage of bigger computers. So people are now talking about exascale computers. I had to look up what exa was. It's the thing that comes beyond whatever, atto or something like that. Atto, right? It's big. And the problem is that the current methods, typically the ones that most computational relativists use, after a few thousand processors, they stop making use of adding more processors. If you work really, really hard, devote several postdoc years to tuning your code, you can get it to scale maybe to 100,000 processors. But as soon as you change the machine or try it on another problem, you have to start from scratch again. So this is a big problem. So let me give you some examples where you actually need this high precision. So I mentioned that black hole neutron stars was a candidate for short gamma ray bursts. Well, the way this is supposed to work is the neutron star gets drawn into the black hole, gets tidally disrupted, most of the star gets sucked into the black hole, but some of the matter remains on the outside as an accretion disk. And then there are various mechanisms where the accretion disk might produce the gamma ray burst. Well, the mass of the disk that's left behind is a few percent of the initial mass of the neutron star. If your overall accuracy is only 1%, then your error in the properties of the disk is 100%. You can't say anything about what the disk is really doing. Now, it's not quite as bad as I make out, but you get the sense, right, that if the phenomenon you're interested in is a small part of the overall picture, you need high accuracy to resolve that particular phenomenon. Similarly, the supernova problem, right, where we have some kind of collapse of a core that makes a supernova. This problem has been tackled by computational means for over 50 years and still is not agreed on the solution. And part of the reason this is difficult is that the initial configuration, the core of a massive star, you have a balance between the gravitational potential energy and the internal energy of the matter. They're balanced to within 1% or so. And so when this thing implodes, if you want to decide whether you get a bounce and a shock or whatever story you want to tell about how the explosion is being driven, you have to be more precise than that 1% difference in order to be able to get a believable result. Another example is one of the goals of LIGO, or of gravitational wave detection in general, is if you have, say, a signal from two inspiraling neutron stars, you should be able to distinguish that signal from two black holes that are inspiraling, because in the case of neutron stars, you should see a tidal deformation of the objects as they get close together. And that should be measurable in the waveform. Well, and if we could do this, we would be able to say something quite definitive about the equation of state of nuclear matter, which is basically an unsolved problem from first principles. So, in order to do that, you have to be able to predict the size of the tidal effects, which are smaller than 1% of the overall waveform that you're trying to look at. So again, you need high precision to be able to do that. Also, you can be misled by having not enough resolution, having errors, say, of order 1%. You can be misled completely. For example, magnetic fields become important in describing the structure and evolution of these accretion disks. And there are magnetic instabilities. MRI stands for magnetorotational instability. That if you don't have sufficient resolution, you don't even see the instability. It's only when your resolution is small enough to resolve the scales of this instability that the effect is there at all. So there are all kinds of reasons why we need to go beyond this. Why is it hard? Well, as I said, there are shocks and surfaces. The solution isn't smooth. There are multiple time scales. There are dynamical time scales of stars. There's time scales, longer time scales for the gravitational waves. All kinds of multiple spatial scales. The geometry changes. You can have a disruption. You can have two objects merging into one. And, of course, all the multi-physics that needs to be done. So currently, we have finite differencing as our standard tool, which I said is not going to be able to do all these things. And also, especially with multi-physics, we have different ways of doing finite differencing for each kind of physics. And then when you try to put them all together, it becomes very complicated. Fortunately, there is a solution. Okay? It's called discontinuous Galerkin methods, which I'm sure most of you have never heard of. Right? So DG is the acronym. So the one thing that you should leave when you go to the tea break, the one thing to remember is DG. Right? It's the answer to everything. So basically, this is a technique that's been developed largely by applied mathematicians. It's actually about 30 or 40 years old, but it's, especially in the last decade, has sort of really flourished. And let me explain to you the idea. So in a finite difference or a finite volume method, you have some cells, which I've shown 3 of them at the bottom here, and then you think of a grid point at the center of each cell that represents the average value of your solution in that cell. So that's shown by the flat blue line. And that's an approximation of the green line, which is the true solution. Now, you can see there's a problem to connect one cell to the next. And the way that's done is you're typically solving something which is a conservation law. So there'll be a flux of the solution from one cell to the next. And you connect the cells by basically using the flux from the left into the right to tell you the recipe for making that connection, and similarly in the other direction. And the beauty of the power of this method, the reason it's worked so well for so many years, is it can handle shocks, because the discontinuities can be modeled with the flux. The drawback of this method, the reason it doesn't scale to big machines, is that if you want to get high order, since you only have one grid point in each cell, the way you have to get high order is you have to couple together many cells. And as soon as you have something that's non-local in the computer, and you have to communicate information, the fluxes from here to a cell which is on some processor over there, when you scale up to millions of CPUs, that becomes inefficient. How does a spectral code work? Well, I said the solution is expanded in local basis functions. So here I've shown 2 basis functions, a constant and a linear function of x. So we represent our solution as a linear combination of those, so basically straight lines. Right? So you see 3 straight lines. This gives you the exponential convergence, but we still have a flux reconstruction problem, and it turns out that for these methods, you can't handle shocks. Okay, it's a little technical, but you take my word for it. The DG code combines these 2 ideas. So again, we have a local basis that lets us get high order by having many basis functions locally, but the fluxes are more general than in spectral methods. In fact, you can use most of the fluxes that are used already in the finite volume methods, so you can handle shocks. And the power of this method is that it's local. You see, you get the high order by just having locally on one processor many grid points, many basis functions. So it will scale well to big machines. So here's a little test example by a graduate student at Cornell. Basically, it's a relativistic inflow. You don't have to worry about the details. It's a standard test problem for shock waves, and you can compare this with other solutions in the literature, but you can see it can handle the strong shocks, interacting shocks and contact discontinuities. Now, the challenge of going to big machines for the future is not simply having methods that are local, that don't need communication. There's another important ingredient, and that's how you parallelize, how you take advantage of all the processes. Basically, as far as I know, essentially every problem that's with PDEs in astrophysics right now is parallelized by taking your grid and dividing it up into little cells and assigning each cell to a processor. When you do that, you introduce artificial internal boundaries between neighboring cells. So you have the communication problem. And if you get bigger and bigger grids, and especially if you think about it in 3 dimensions, there's no way to always have very close communication. You'll be wanting information just because of your artificial boundaries from distant processes. And that, again, spoils the scaling. There's another way to parallelize, and it's called task-based parallelism. You divide your problem up into a bunch of tasks that need to be performed. So you can still divide up your grid, and you can say, all right, I need to calculate some derivative locally on this grid. All right, that's a task. I also need to send information to that processor over there so it can handle this artificial boundary that I've introduced. That's another task. So what you do is you set up a master controller processor which has the list of tasks, and when you have an idle processor, you assign the task. So you ship out your tasks. So while this task of sending data to some distant processor is going on, other useful work can be done. You're not sitting waiting for some information to arrive. So with task-based parallelism, you have the hope of being able to scale again to large numbers of machines. All right, especially for astrophysics, this is important because we want to do very inhomogeneous tasks, tasks that take different amounts of time. We might have a neutron star where somewhere in the center there's a very complicated equation of state calculation that needs to be done to figure out what the pressure is for that given density. Whereas in another region of the neutron star where the density is lower, we might have a simpler calculation that takes less time. In current computer methods, you have to wait for the slowest guy to finish before everybody can advance. With task-based programming, you don't have to do that. All right, so here's a problem that we've done to illustrate this. The thing that makes this difficult is there are no standard packages. It's very difficult to program task-based parallelism, but I predict it will actually become easier. All right, so here's a test problem of some interacting vortices run on blue waters, which is a big machine. And you can see at the bottom is plotted the number of processors, and then along the vertical axis is the speed up. So we take a fixed amount of computing that needs to be done. We assign more and more processors to it. And if we have perfect scaling, this should be a straight line. And you can see it is essentially a straight line. There's a little glitch at the end because we didn't choose a big enough problem. So the scaling sort of starts breaking down a bit over there. Now, this is extremely exciting for anybody working in computational astrophysics because to get this kind of scaling with traditional codes, as I said, takes several person-years of effort. We got this, or I should say Scott Field, who's a postdoc at Cornell, got this in one day. Took our code from his laptop, put it on blue waters, fiddled around with the settings in one day, and got this scaling. And that's because we have task-based parallelism. Okay, so I think this is really revolutionary. I'm very excited about it. Okay, let me skip over this things here. Let me just say, this is only the beginning of the problem. There are lots and lots of challenges, how to do the scaling, how to choose the things, and so there's a help wanted sign. I'm encouraging people who are interested in this to talk to me. I think that more and more people in astrophysics should get involved with this. So let me just end with this beautiful picture. This was made by some of my graduate students when they were supposed to be working on their theses. One of them had developed a ray tracing code, and so they made this image. In the middle are two black holes. You can see unequal masses. They're from our calculation of orbiting black holes. The background is a realistic star field from a catalog, so these are real stars. The colors of the stars are from the catalog. They are appropriately redshifted if they come near to the black holes and they travel out back to us. And you can see the gravitational lensing effects. So for example, The fact that the black holes are not spherical is because they're rotating, and the light rays that come on the one side have a frame dragging effect towards us, and on the other side away from us. And you can see those sort of things which are technically called eyebrows. Those come from rays which, if you trace back from us, they go around the black holes and then come into the black hole, so they don't, we don't see stars, they're black. And then if you look you can't see it on this image, but if you look very carefully, there are eyebrows on the eyebrows from rays that go around twice before they go in. And then you can see that sort of ring-like structure. That's the Einstein ring that people who've looked at gravitational lensing from a point mass know about here. You can see the analog of that from this binary system. And the point I want to make is, so by the way, if you want to see a movie of this, there's an animation of where the black holes are orbiting. You can go to YouTube and find it. It's already been downloaded over 200,000 times. It's very popular. And the thing I want to emphasize is that this is not an artist's conception, right? Every detail here is calculated from the full 3+1 dimensional general relativity. The simulations of the black holes, the ray tracing, everything is done precisely. And I think it's remarkable that in 100 years, right, we've gone from the Einstein writing down the equations to our ability to solve to this level of complexity what the theory predicts. Of course, there's no hope of seeing this, of observing anything like this right now, but who knows, at the 200th anniversary, maybe in this very hall, right, somebody will show observations that look like this. Thank you.